Hey everyone, in this next sequence of videos we are introducing the idea of impulse, which will very quickly get us into momentum, a very well-known and important physics concept. Okay, let's go ahead and get into it. When you were watching our last sequence of videos about energy, if you remember, we were actually starting off by looking at Newton's second law, and then we actually plugged in an equation and saw what happened when there were forces and distances. And with the net force, that led to the work-energy theorem, things like that. We're going to do something similar in that we're going to start with Newton's second law, and we're going to see where that gets us if now instead of plugging in one of those constant acceleration equations, we plug in something a little different. So let's go ahead and get started. What I know by Newton's second law is that the net force acting on an object, I could write this as sigma F, but just to keep things maybe a little nicer, let's just write F with a little net, okay? F net is equal to the mass of an object times its acceleration, right? Well, what is the acceleration of an object? It's its change in velocity divided by t. Let's plug that in right there. That means that the net force on an object is equal to its mass, of course that's not changing, times delta V divided by t. Now technically, remember, this is like delta t as well. It's the change in t, but we pretty much always say t0 is 0, so that's why I just have single t right there. Makes our lives a little easier. Okay, what I'm going to do next, two things. I'm going to swing this time to the other side, and then that way it'll allow me to, number two, get rid of these parentheses. So I have the net force multiplied by t is equal to m times delta v. And remember, delta v is v minus v naught. So, oh my gosh, F net times t equals mv minus mv naught. I may be skipping a step, like I would put this in parentheses, v minus v naught, but this is, saving us maybe a couple of seconds. This right here is known as the impulse equation. The net force on an object multiplied by time, say the time of that net force, is equal to mv minus mv naught. Now, there's a couple things I want to point out in this equation. Number one, technically, this is sometimes labeled as J. J meaning impulse. I'm not sure why they use the letter J. You could probably Google an answer. But J represents impulse. You might be asked, what is the impulse for a certain maybe impact? Or when a force is acting upon an object, calculate the impulse. And you could do that by taking the net force on the object and multiplying it by t. Likewise, you could do this mv minus mv naught thing and also find quote-unquote the impulse. Now, that's actually pretty rare. Even though this is called the impulse equation, technically these two things multiplied by each other are or is impulse. Pretty much no one asks to calculate the impulse. This is actually how the equation is mostly used, to relate force, time, mass, and velocity. Okay, so it's the impulse equation, but normally we're just thinking about it in terms of forces, times, m's, and v's. Okay? What's the other thing that's important? Well, oh my gosh, very similar to what we saw when we applied the work-energy theorem. When I do this very simple derivation, I notice something. Something pops up. These two terms, something about an object when there's a net force that's applied to it for an amount of time, something about this object related to its mass and its velocity is changing. I have this v and then this v naught. I have some initial quantity, whatever the heck this is, and some final quantity. And this always pops up whenever we are applying net forces for some amount of time. Just like before, how that kind of indicated importance, and that's where the term kinetic energy comes from, this here is indicating importance. This is where the term momentum comes from. Momentum is the word that is used to describe this change. When you apply a net force for an amount of time, something about the object changes. What do we call that? Just because it's so important, it keeps showing up over and over in every different scenario you can think of. So physicists give that a name, momentum. So that's where momentum is coming from. Here it is in this impulse equation. Okay? In another video, you're going to see some implications for this impulse equation, but for the rest of this one, let's just jump down and understand what momentum is, go over a couple of facts about momentum. So there's the equation. Again, now it's just kind of isolated, kind of like how I could isolate the kinetic energy equation. Okay, so here it is all isolated. Yeah, when you apply a force for a certain time, there's a change in momentum, but also an object could have some momentum at any given moment based on its mass at that moment and its velocity. So momentum is a property of objects with mass and velocity. So it's a property of moving objects based on, well, those two things. Often if you read physics textbooks, it's defined as inertia in motion. Inertia relating to the mass, and motion, of course, relating to the velocity. This is, I don't know, it's kind of roll your eyes adorable, but it's not really important. Okay? It's a property that moving objects have. Moving objects have this thing known as momentum. Now, some of you are going to dislike this. Momentum is a vector, which technically means if you have some ball, let's say moving this way, has some mass, has some velocity, it has some momentum like this, you could break it back down into components and look at momentum in the x direction and momentum in the y direction. On the bright side, for AP Physics 1, we are not looking at multi-dimensional or two-dimensional momentum. We're only going to deal with momentum 99% of the time, dealing in or going in a single direction. So it is technically a vector. Okay? If you say to the right is positive, an object going right would have positive momentum, an object going left would have negative momentum. But we're not going to be worrying about breaking things down again. That still is kind of behind us after our force unit. But momentum is a vector, unlike energy. So direction does matter. Now the unit for momentum, well, mass, that's measured in kilograms. Velocity, that's measured in meters per second. So the overall unit for momentum, it has to match the equation, and here it is. It's kilograms meters per second. There is no special name for the unit for momentum. It's not named after any other scientist. I like to joke with my students that after some of you, make it big, you become world famous physicists, and you solve major world problems, or you make huge contributions to science. Well, maybe you think back to your old friendly YouTube video host Thrasher here, and maybe you rename the momentum unit after me. I would love it if, what's the momentum of the object? It's 5 Thrashers. I'm not going to get there on my own. I'm not that talented, but maybe one of you will one day, and you'll name it after me just because of all the help I've given you. Anyway, that's it. That's the basic idea behind impulse and momentum. Of course, we will be building off of these ideas in future videos. But that's all. Pretty quick video right here. Thanks for watching.